Hi there, my name is JJ Nahara, and welcome to my Secure Network Architecture Design Screencast. To begin, let's look at the core components of the secure network design. The environment is built within virtual blocks, using multiple virtual machines that represents different layers of a corporate network. Also, as just a disclaimer, I do not have a camera with the computer that I actually run all of VirtualBox and the VMs on. So the camera that I've been using has been on my other computer, and there's no way to get the environment to there, so there's not going to be video for this screencast. Anyways, at the perimeter, I have a pfSense firewall appliance, which functions as the first line of defense against unauthorized access. pfSense enforces firewall rules, manages network address translation, or NAT, and provides segmentation between the internal network and the external internet. To simplify management, I access the pfSense firewall GUI directly through my Kali Linux VM. As seen here, I just go to Firefox, and then I go to the pfSense address, sign in, and here it is, which allows me to create rules, monitor network traffic, and apply filtering policies. Inside the protected network, the Windows Server 2019 VM is configured as the domain controller. In addition to providing Active Directory services and authentication, this server also hosts both the DNS server and the DHCP server. This combination ensures that client devices such as my Windows 10 and Windows 11 machines can automatically receive IP addresses and resolve hostnames when joining the whatever.com domain. By centralizing directory, DHCP, and DNS services on the Windows Server, the infrastructure is able to provide secure authentication, reliable IP assignment, and internal name resolution. So if we just come here, we see my Windows Server 2019, and we see how we have the Active Directory, DHCP, and DNS servers also installed on this, which is a domain controller as well. Or else it would say a little yellow triangle right here that would say promote to a domain controller, but we've already done that. Supporting these services are my additional machines. If we just come here to Oracle VirtualBox, my Windows 10 and my Windows 11 clients act as domain joined systems that authenticate to the server for network access and policy enforcement. On the Linux side, I have Ubuntu and Parrot Security OS, which serve as flexible testing and research platforms, with Parrot specifically geared towards penetration testing. Together, these diverse systems represent the multi-platform nature of enterprise networks. Now, let's talk about how all these pieces interact with one another. When a client machine boots up, the DHCP service on the Windows Server 2019 VM assigns it an IP address and provides the DNS configuration. The DNS service then allows the client to resolve domain names both internally and externally. Authentication requests from the clients are sent to Active Directory Domain Controller, which uses Kerberos for secure encrypted credential validation. Meanwhile, all inbound and outbound network traffic flows through the pfSense firewall. Its firewall rules block unauthorized access while allowing permitted traffic, such as domain logins or web browsing. If any traffic needs to be filtered or rules updated, I can log into the pfSense web GUI via my Kali Linux VM. Again, we can go back here and see it. Also, just so you can see, here is my pfSense firewall. I can do 8 here to get to the shell, do commands from here, stuff like that. But yeah, I can log into the pfSense web GUI via my VM and manage it in real time. This makes Kali not only a penetration testing tool, but also a central management station for network defense. The Linux-based servers, such as Ubuntu and Parrot Security OS, are isolated within the same internal VirtualBox network. They interact with the rest of the infrastructure through controlled ports and protocols, ensuring segmentation and reducing lateral movement opportunities in case one machine gets compromised. Finally, logs are collected across the infrastructure for analysis. The firewall servers and clients all generate logs that can be correlated to detect suspicious behavior. This centralized monitoring is essential for detecting patterns of attack that might otherwise go unnoticed. As seen in our IDS and IPS labs, we've configured that as well using things like Suricata. When it comes to the pfSense firewall, I not only rely on it for perimeter defense, but also for fine-grained control of traffic inside my lab. Using the pfSense web GUI, which I access from Kali, I can configure rule sets to define exactly what traffic is allowed for in and out of each network interface. For example, I've created rules to only permit domain traffic between the Windows clients and the domain controller while restricting unnecessary ports that could be exploited. In addition to rules, pfSense generates detailed logs for each decision it makes, whether a packet is allowed, blocked, or dropped. By reviewing these logs, I can correlate firewall activity with the authentication logs on the Windows server or system logs on the Linux machines. Next, let's turn our attention to the security issues and implications of advanced and novel networks and protocols. One major issue is the complexity of emerging protocols. For example, with the adoption of IPv6, networks often operate in dual stack mode, supporting both IPv4 and IPv6, but misconfigurations in IPv6 can allow attackers to bypass security controls or launch stealth attacks. Another challenge comes from software-defined networking, or SDN, which centralizes traffic control using controllers. While SDN provides flexibility and dynamic configuration, it also introduces a single point of failure. If the controller is compromised, the attacker gains control over the network's routing. Virtualization and cloud-based environments also both bring advantages and risks. Virtualization, as I've demonstrated in VirtualBox, allows for isolated environments with easier testing, but hypervisor vulnerabilities can lead to VM escape, where an attacker moves from a guest machine into the host. Similarly, cloud misconfigurations often expose data or services directly to the internet, creating a major attack surface. Protocols like QUIC using HTTP/3 encrypt more of their traffic by default. This is good for privacy, but it makes network monitoring and intrusion detection much harder, since traditional tools rely on inspecting unencrypted headers. The trade-off between privacy and visibility continues to challenge modern network security. Let's just see what time we're at. Come here. 6 minutes. Got it. So as we wrap up, finally, with the explosion of IoT devices, networks face additional risks. Many IoT devices lack proper hardening and can be exploited to gain a foothold in an otherwise secure network. The Mirai botnet is a clear example where insecure IoT devices were hijacked to launch massive denial of service attacks. So in summary, my secure network design incorporates multiple defense layers, including pfSense for perimeter security, Windows Server 2019 for centralized authentication, DNS and DHCP, and a mix of client and Linux servers for testing and operations. These components work together to provide a functioning enterprise-like environment with proper segmentation and monitoring, and at the same time advanced and novel networks such as those using IPv6, SDN, QUIC, and IoT bring both opportunities and new risks that organizations must account for. Thank you so much for tuning in to my screencast, and I hope you like the environment that I've created.